Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR, Enterprise Core exam. This course will cover all topics you need to know to pass the ENCOR exam. In this video, we will look at VLANs, virtual LANs, which are used to segment a network at layer 2 by dividing a switch into multiple virtual switches. Most of this video will be review from the CCNA, but we will also cover some additional information to bring your understanding of VLANs to a CCNP level. Here's what we'll cover. First, I'll give an overview of VLANs and their purpose. Then, we'll look at how to create VLANs on Cisco switches. We'll also cover how you can shut down and suspend VLANs, and the difference between the two. Then, I'll mention internal VLANs, which are VLANs the switch automatically creates for its internal use. Next, we'll cover access and trunk ports, and finally, Inter-VLAN routing using an external router or a layer 3 switch. Let's get started. VLANs are used to segment a LAN into multiple virtual LANs, multiple broadcast domains. Without configuring VLANs, all hosts connected to the same LAN are in the same broadcast domain. That could mean all connected to the same switch, as in the diagram below, or connected to different switches, but the switches are connected to each other. In this case, all hosts are in the default VLAN, which is VLAN 1. Actually, rather than saying that the hosts are in VLAN 1, it's more accurate to say that all switch ports are in VLAN 1, because the hosts themselves aren't aware of what VLAN they are in. They just send and receive untagged frames. The VLAN is a configuration on the switch port. In a very small network, this setup might be acceptable, all hosts in the default VLAN. However, anything beyond a SOHO network will probably use VLANs. Even in small networks, it's common to segment the network using VLANs. Even if the network is segmented at layer 3, meaning different subnets are used, if VLANs aren't used to segment it at layer 2, broadcast and unknown unicast frames will be flooded to all hosts. So, PC1 and PC2 are in a subnet, PC3 and PC4 are in a subnet, and PC5 and PC6 are in a subnet. However, they're all still in VLAN 1. So, what happens when PC1 sends a broadcast frame? Switch 1 floods it out of all ports, regardless of the subnet of the end host. Although the network is segmented at layer 3, it is not segmented at layer 2. It is one broadcast domain. To properly segment the network, we should combine VLANs and subnets. Usually, one VLAN equals one subnet, although not always. Later, we'll see how multiple subnets can be used in a single VLAN. It's not so rare. In this case, VLAN 12 is 10.0.12.0/24, VLAN 34 is 34.0/24, and VLAN 56 is 56.0/24. By configuring VLANs, the switch is split into multiple virtual switches. The switch will not forward or flood a frame to interfaces in a different VLAN than the one it was received on. This time, when PC1 sends a broadcast frame, switch 1 only floods it out of G00 and G02. Assume in this case that the connection between R1 and switch 1 is a trunk, using router on a stick. Switch 1 is a layer 2 switch, so it's not doing the inter-VLAN routing itself. The network is now segmented at both layer 3 and layer 2. Here's another way to illustrate that same network. The white box in the middle represents the physical switch 1, and it is divided into 3 separate virtual switches. One for VLAN 12, one for VLAN 34, and one for VLAN 56. These virtual switches are not directly connected, and hosts in one VLAN cannot communicate directly with hosts in another VLAN. If PC1 sends a broadcast frame, it is only flooded out of interfaces in VLAN 12. For hosts in different VLANs to communicate with each other, the traffic must be routed via a router, or using a multi-layer switch. We will review inter-VLAN routing later in this video. Next, I want to cover the topic of stretched VLANs. The details of this topic are related to network design, so if you want to learn more, you can consider the ENSLD exam after ENCOR. That exam is dedicated to network design, and it's one of the specialist exams you can take to complete your CCNP Enterprise certification. Anyway, stretched VLANs are VLANs that span multiple sites. In the diagram below, VLANs 12, 34, and 56 are stretched across the three sites, which are connected via trunks that allow VLANs 12, 34, and 56. So the whole network is one layer 2 domain, although it is split up into three VLANs. Hosts in each VLAN are all in the same subnet, regardless of site. Hosts in VLAN 12 are in subnet 10.0.12.0/23, hosts in VLAN 34 are in 34.0/23, and hosts in VLAN 56 are in 56.0/23. This kind of design is generally not preferred in modern networks. We want to minimize the size of broadcast domains. With this design, if a host at site 2 in VLAN 56 sends a broadcast frame, it will be flooded to all hosts in VLAN 56, in sites 1, 2, and 3. Like I said, this kind of design is usually not preferred. The preferred design is to use local VLANs. Notice that the distribution switches at each site are now multi-layer switches, and the connections between sites are layer 3 connections. Local VLANs are localized to a site, and connections between sites are layer 3, so VLANs do not pass between them. Site 1 is its own layer 2 domain, same for site 2 and site 3. Each site has its own VLAN 12, VLAN 34, and VLAN 56. Note that it doesn't matter if the VLAN numbers are the same or different at each site. The VLAN numbers are locally significant to each site. However, it may be desirable to use the same VLAN numbers at each site for consistency. For example, perhaps end users at each site use VLAN 12, security cameras use VLAN 34, and servers use VLAN 56. Or you could use different VLAN numbers at each site. It's up to whoever designs the network. In any case, each VLAN should be its own subnet. For example, Site 1 could use 10.1.12.0, 34.0, and 56.0/24. And Site 2, 10.2.12.0, 34.0, and 56.0/24. And Site 3, 10.3.12.0, 34.0, and 56.0/24. This kind of design is usually preferred over the previous one, in which the VLANs and subnets stretch across all three sites. Like I said, if you're interested in learning more about network design like this, consider the ENSLD exam after ENCOR. Next, let's look at the topic of using multiple subnets per VLAN. Generally, one VLAN equals one subnet. However, as you progress in your studies, you'll find cases where general rules you learned in the CCNA are broken. So, when would we use multiple subnets per VLAN? If all addresses in a subnet have been used, you can add a new subnet and associate it with the same VLAN. For example, in the diagram below, I show two VLANs. VLAN 10 is for end users, and VLAN 20 is for security devices like cameras, door locks, etc. However, what happens if the company is expanding and we have run out of addresses for end users? We can simply add another subnet, 10.0.3.0/24 in VLAN 10. Let's see how to implement that. If using an SVI for routing, configure a secondary IP address on the VLAN's SVI. Or if using router on a stick for routing, configure a secondary IP address on the sub-interface for the VLAN. For example, as you can see here on switch 1, it has an SVI for VLAN 10, 10.0.1.1, and an SVI for VLAN 20, 10.0.2.1. Let's add a third SVI for the new 10.0.3.0/24 subnet. That's it. Make sure to add it as a secondary IP address. Now, how will hosts in 10.0.1.0/24 and 3.0/24 communicate with each other? Although they are in the same VLAN, they are different subnets. So, for hosts in each subnet to communicate with each other, traffic will have to be routed by switch 1. For example, for a host in 10.0.1.0/24 to send a packet to a host in 3.0/24, it will send the packet in a frame to the MAC address of switch 1's VLAN 10 SVI, and then switch 1 will forward it in a frame from the MAC address of the VLAN 10 SVI. So the packet is received on and forwarded out of the same SVI. Now let's review how to create VLANs. To create a VLAN, use the VLAN command. Keep in mind that this is different than creating an SVI, which uses the interface VLAN command. The VLAN command creates the VLAN itself, which is a layer 2 entity, whereas an SVI is a layer 3 interface associated with the VLAN. Note that after using the VLAN command, the VLAN isn't actually created until you leave VLAN configuration mode, or use the VLAN command again to make another VLAN. Let's confirm that. On a switch, I used show VLAN brief, and it only has the default VLANs. To save space, I'm not showing all of the VLANs. Then I used the VLAN 10 command to create VLAN 10, and also gave it a name, end users. I viewed the VLANs again, but VLAN 10 doesn't appear. To create the VLAN, I use the exit command and check the VLANs again. This time it appears. So that's how to create a VLAN. It's pretty simple. To delete a VLAN, just use no in front of the VLAN command. And by the way, when creating and deleting VLANs, you can specify a range instead of a single VLAN. For example, VLAN 100 to 105, 120, 131 will create those 8 VLANs all at once. You can also shut down and suspend VLANs. Those might sound like the same thing, but they are a bit different. Use the shutdown command on a VLAN to disable it on the current switch. This means the switch will not forward traffic in the VLAN. Let's try it out. On switch 1, I used shutdown in VLAN configuration mode. Just like when creating a VLAN, this doesn't take effect until you exit out of VLAN configuration mode for this VLAN. So I used exit and then checked the VLANs. Notice that in the status column it says act/lshut. lshut means locally shut down. The VLAN is active in the VTP domain, but disabled on the local switch. So to shut down a VLAN is to disable it on the local switch. However, you can use the state suspend command to disable it in the entire VTP domain. The VLAN will not be deleted, but all switches in the VTP domain will not forward traffic in the VLAN. If you need to temporarily disable a VLAN across the network, this is the appropriate command. So I used no shutdown to re-enable VLAN 10 on switch 1 and checked the options for the state command. Use state suspend to suspend the VLAN, and then state active to reactivate it later. I used state suspend, exited VLAN config mode, and checked the VLANs. As you can see, VLAN 10 is now in the suspended state. That change was propagated to switch 2, another switch in the same VTP domain as switch 1. So remember the difference between shutdown and state suspend. Shutdown disables the VLAN on the local switch, but does not affect it on other switches. State suspend disables the VLAN in the entire VTP domain. Now let's move on to the topic of internal VLANs. In some cases, Cisco switches create internal VLANs for their own use. The most common example is when you make a routed port with the no switch port command. Each routed port uses an internal VLAN. Internal VLANs are created from the extended VLAN range, starting from 1006 by default. You can control this behavior, however. The command is VLAN internal allocation policy, then ascending or descending. Ascending is the default and means that allocation starts from VLAN 1006. Then after that would be 1007, 1008, etc. Descending means that allocation starts from 4094, then 4093, 4092, etc. Note that internal VLANs will not appear in the output of show VLAN brief, etc. But you will not be able to use the internal VLANs for other purposes. Let me demonstrate that. On switch 1's G01 interface, I used no switch port to make it a routed port. Then I used show VLAN brief, include 1006, and there is no output. However, when I try to make VLAN 1006, it fails, displaying a few error messages. Some syslog messages are shown too. Notice that it says VLAN 1006 is currently in use by Gigabit Ethernet 01. To view the switch's internal VLANs, use Show VLAN Internal Usage. As you can see, VLAN 1006 is being used by the G01 interface, a routed port. If you're in a situation like this, but you have to use VLAN 1006 on the switch, here's a quote from Cisco on how to solve that problem. If necessary, you can shut down the routed port assigned to the internal VLAN, which frees up the internal VLAN, and then create the extended range VLAN and re-enable the port, which then uses another VLAN as its internal VLAN. So, when planning VLAN numbers in a network, just be aware of internal VLANs and design your VLAN numbering to avoid internal VLAN numbers, especially if you are using routed ports on your switches. Now let's move on to access ports. This is review from the CCNA, so we'll cover it quickly. Access ports, also called untagged ports, are switch ports which belong to a single VLAN, and send and receive untagged traffic. Because the port is associated with just a single VLAN, there is no need to include a .1q tag to indicate which VLAN the traffic is in. The switch knows without the tag. Although, if a voice VLAN is configured, the port belongs to two VLANs, the access VLAN, which is untagged, and the voice VLAN, which is tagged. Although the port carries traffic in multiple VLANs, in Cisco iOS, it is still considered an access port. Ports connected to end hosts should usually be access ports. Here's an example network. The ports connected to end hosts, with the colored cables in the diagram, are access ports. On the other hand, connections between network infrastructure devices use trunk ports. The connection between switch 1 and switch 2 is a trunk, and so is the connection between switch 1 and R1. That is because traffic in multiple VLANs must pass over those connections, so a tag is required to identify which VLAN traffic belongs to. There are exceptions to the rule that ports connected to end hosts should be access ports. For example, servers running VMs should connect to trunk ports, because each VM on the server uses a different VLAN. Here's an example. A server has three VMs, VM1, VM2, and VM3. VM1 uses VLAN 21, VM2 uses VLAN 22, and VM3 uses VLAN 23. They connect to a virtual switch in the server, which connects to a switch via a trunk port that carries traffic in VLANs 21, 22, and 23. Okay, back to access ports. How can we configure them? Use switch port mode access to configure an access port, and then switch port access VLAN, followed by the VLAN ID to specify the access VLAN. Another option is switch port access VLAN name, followed by the VLAN's name instead of the VLAN ID, which is a number. And then there are similar commands for the voice VLAN. We'll review the configurations in the lab video, so now let's move on. Next up, trunk ports. Like we did for access ports, this is just a brief review from the CCNA. Trunk ports, also known as tagged ports, are ports which carry traffic in multiple VLANs. VLAN tags, using the .1q protocol, are used to indicate which VLAN the traffic belongs to. That's why they are also called tagged ports. Another protocol is Cisco's ISL, but it's been replaced by .1q, and there's no need to learn ISL. Now, not all traffic sent over trunk links is tagged. The native VLAN is an exception, because traffic in the native VLAN is sent untagged. Also, if untagged frames are received on a trunk port, they are assumed to be in the native VLAN. Note that the native VLAN is a feature of .1q only, not ISL, and it's best practice to disable the native VLAN. There isn't actually a command to disable it, but what you can do is assign an unused VLAN as the native VLAN. For example, the network below uses VLANs 12, 34, and 56. So we could make VLAN 99 the native VLAN, for example, since it's not used in the network. It's also worth noting that the native VLAN is an interface-level command. Each interface can have a different native VLAN. Over trunk links, the .1q tag is placed between the source and ether type fields of a frame, like this. It's 4 bytes in length, and here are the fields of the tag. The TPID field is always set to hex 8100. This indicates that the frame is .1q tagged. Next, the PCP and DEI fields are used for QoS, which we'll cover later in the course. And finally, there is the VLAN ID, which identifies which VLAN the frame belongs to. And now, let's review how to configure trunks. We'll practice all of these configurations in the lab, so let's just list the commands for now. First, you may have to specify the trunk encapsulation with switchport trunk encapsulation.1q, or ISL of course, but you probably won't use that. This command is only available on switches that support ISL, by the way, and many switches these days only support .1q, in which case this command is unnecessary. Next, you can configure a static trunk with switchport mode trunk. Note that if the switch supports ISL, you'll need to use the above command first. And you can configure the native VLAN with switchport trunk native VLAN. Again, it's best practice to configure an unused VLAN as the native VLAN, to avoid VLAN hopping attacks. All VLANs are allowed on trunks by default, but it might be a good idea to limit which VLANs are allowed on the trunk with switchport trunk allowed VLAN, followed by one of the options shown here. We'll review these in the lab video, but I will say you should be careful when modifying the VLANs allowed on a trunk. To add a VLAN, remember the add keyword. For example, switchport trunk allowed VLAN 56 will not add VLAN 56 to the list of allowed VLANs on the trunk. It will allow only VLAN 56 on the trunk. So be careful with this command. Okay, that's all about trunks for now. We'll cover some other aspects of trunks in the DTP video. Finally, let's review Inter-VLAN routing. Really, it's just routing between subnets, but with VLANs and VLAN tags involved, there are some extra considerations. There are 3 methods of configuring inter-VLAN routing. Perhaps the simplest is to have a separate connection per VLAN to the router. They don't even have to be trunks, they can be access ports. This is quite rare, since with many VLANs you'll need many interfaces, and routers typically only have a few. The second option is to use router on a stick, which is a trunk connection between the switch and router. Finally, perhaps the most common method is to use SVIs on a multi-layer switch. Generally, you'll use one of these 2 methods, so let's review how to configure them. First up, router on a stick, which is a trunk connection between the switch and router. On the switch, you configure it like any other trunk connection. I allowed only the necessary VLANs on the connection. On the router, you have to configure sub-interfaces, 1 per VLAN. To configure a sub-interface, add a period and a sub-interface number to the end of the interface command. Then, specify the VLAN ID for this sub-interface with encapsulation.1q, followed by the VLAN ID. Finally, configure an IP address on the interface. I did that for VLAN 34 and VLAN 56 too. That's it. Now, switch 1 and R1 can send tagged frames between each other. R1 will route between the VLANs, between the subnets. Just a couple extra points about router on a stick. The router's sub-interface numbers do not have to match the VLAN number. They can be any number, although there's no reason not to match them. It makes things much simpler. And if you are using the native VLAN, you can configure the router's interface in one of 2 ways. The first method is to configure the IP address for the native VLAN directly on the interface itself, not a sub-interface. Traffic to and from this interface will be untagged. The second option is to configure a separate sub-interface for the native VLAN, specifying native at the end of the encapsulation.1q command. Okay, that's all for router on a stick. Finally, let's look at inter-VLAN routing with SVIs. Switch virtual interfaces are virtual layer 3 interfaces inside of a switch. They can be used to perform inter-VLAN routing without a separate router. Multi-layer switches have their own router within the switch. It's like this. With 3 VLANs, switch 1 is split up into 3 virtual switches. And because it's a multi-layer switch, it also has a virtual router inside of it, with 3 interfaces, SVI 12, SVI 34, and SVI 56. Hosts in different VLANs can communicate with each other via that virtual router. And a Layer 3 connection to another router may be used for routing to external networks. Routers provide more functionality, like NAT, so switch 1 might connect to R1 via a routed port like this, perhaps for an internet connection. Let's see how to configure this setup. First, enable IP routing on switch 1 and configure a route to R1. It doesn't have to be a default route, it depends on the network, of course. To configure the routed port, use no switch port and then configure an IP address. Now, we just have to configure the SVIs. The command to configure an SVI is interface VLAN followed by the VLAN ID. Then, just configure an IP address on the SVI. And that's how to configure Inter-VLAN routing using SVIs. Here's what we covered in this video. We reviewed VLANs, how to create them on a switch, how to shut down and suspend VLANs, remember the difference between those two. We also looked at the concept of internal VLANs, and then reviewed access and trunk ports and Inter-VLAN routing. As I mentioned at the beginning of this video, most of the material in this video was review, but we did cover some new concepts as well. VLANs are part of the ENCOR exam, of course, so it's worth reviewing them. We will look at the configurations more in the lab video, and in upcoming videos, we will dig deeper into VLAN-related topics like DTP and VTP. Okay, now let's go on to the quiz to test your understanding. Here's quiz question 1. Which of the following describes the minimum requirements for complete connectivity between VLANs? ROAS has already been configured. Pause the video now to think about the answer. Okay, the answer is D. Create VLANs 12, 34, and 56 on switch 1, and VLANs 12 and 34 on switch 2. Allow VLANs 12 and 34 on the connection between switch 1 and switch 2. That enables full connectivity between all VLANs. Switch 2 doesn't require VLAN 56, because traffic in VLAN 56 will never have to pass through switch 2. Switch 1, on the other hand, does require VLAN 12, even though no hosts in VLAN 12 are connected to switch 1. That's because switch 1 is connected to R1, and traffic in VLAN 12 must reach R1 for inter-VLAN routing. Only VLANs 12 and 34 need to be allowed on the connection between switch 1 and switch 2 because, once again, traffic in VLAN 56 will never have to travel across that link to switch 2. Let me demonstrate. Let's say PC5 in VLAN 56 sends a message to PC1 in VLAN 12. PC5 sends it untagged to switch 1, which forwards it tagged as VLAN 56 to R1. R1 routes the packet and sends it back to switch 1 tagged in VLAN 12. Switch 1 forwards it to switch 2 tagged in VLAN 12, which forwards it to PC1. So even though PC5 is in VLAN 56, when PC5's message travels between switch 1 and switch 2, the message is no longer in VLAN 56. It has already been routed to VLAN 12 by R1. If PC1 replies to PC5, the message will again be tagged in VLAN 12 when it travels from switch 2 to switch 1. There is no need to allow VLAN 56 over that trunk. Okay, let's go to question 2. You issue the following commands on switch 1. Those are VLAN 100, then state suspend, then exit. Which of the following statements best describes the status of VLAN 100? Pause the video now to think about the answer. Okay, the answer is B. All switches active in the VTP domain will not forward traffic in VLAN 100. This command will put the VLAN in a suspended state, and also propagate that status to all switches in the VTP domain. It will not delete the VLAN, so it will not remove VLAN 100 from any switch's VLAN database. Note that the shutdown command is similar to the state suspend command, but only takes effect on the local switch. Okay, let's go to question 3. You issue the following commands on switch 1 and receive some error messages. The commands are VLAN 4094 and then exit. and you can read the messages below. Which of the following statements are true? Select 2. Pause the video now to think about the answers. Okay, the answers are A and C. VLAN 4094 cannot be created because it is being used as an internal VLAN. Switch 1G01 is a routed port, and each routed port on a switch uses an internal VLAN to function. So C is correct. A is also correct because, by default, internal VLANs are assigned ascending from VLAN 1006 in the extended VLAN range. In this case, VLAN 4094 is being used, so that means someone configured VLAN internal allocation policy descending on switch 1. Okay, let's go to question 4. R1 uses router on a stick to perform inter-VLAN routing, tagging all traffic on its G00 port. VLAN 10's current subnet has run out of addresses. Which of the following configurations adds another subnet for VLAN 10? Pause the video now to think about the answer. Okay, the answer is C. Interface G00.10 to configure the subinterface, and then configure the IP address with the secondary keyword. A and D configure the physical interface, not a subinterface. However, the question states that all traffic is tagged, so that means VLAN 10 is not the native VLAN. So the configurations must be on a subinterface, not the physical interface. And B is wrong because it doesn't specify the secondary keyword. If you don't specify secondary, the IP address command will not add another address to the G00.10 subinterface. Instead, it will overwrite the current IP address, which is not what we want. We want to add another address, not overwrite the current one. Okay, let's go to question 5. You issue the following commands on switch 1. VLAN 10, VLAN 20, VLAN 30, and finally VLAN 40. How many non-default VLANs exist on switch 1 after the final command? Pause the video now to think about the answer. Okay, the answer is B, 3. VLANs 10, 20, and 30 exist on switch 1. VLAN 40 does not yet exist. Although you are in VLAN config mode for VLAN 40, VLAN 40 isn't actually created until you exit VLAN config mode, or enter VLAN config mode for another VLAN. That's a little quirk about creating VLANs in Cisco iOS. Okay, that's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Yonatan Makara, Velva Jacob, George Streeter, Funny Dart, Nasir Chowdhury, Devin Suku, Gustavo B.R., Gerard Baker, Marcel Lord, Pavel M., Mr. Erlison, Dragos Hirnea, Zakib Shah, Mayor Salman, Mazen Anderson, Vitaus194, Gina Lindley, Mark Jackson, Bold1C1U, Michael Carroll, Gerald Guillaume, Gabriel Braga, Hector Hernandez, Maratuba, Roji Kuriakos, Arpad Konives, 5 Feet, Owad, Daniel Brown, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, Hussein Yavuz, Samuel Tavares, Roger Bratseth, Mustafa Ursoy, Dear Diso, Nasser Zahar, Brian Grant, Alexandru Badic, Georgi Gemejev, Dibya Swain, Arlen Plagaria, Adelson Pereira, Farad69, Lucian Stoichitoyu, Madmark 50484, Sean Powell, Alexandru Stratton, Hiago Bicalho, Abdo Zizo, Piotr Kaimov, Abubakar Berry, Jeremy You Are Really Really Great, Kurt Nell, Preeti Dongave, Omid Farakash, Steve Cox, Joe Black, Jasper Yim, and Wilmer Romero. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.